Here we have two additional examples. The first one, formation of rust or synthesis of iron 3 oxide. We've already balanced the equation, so I'm going to go ahead and fill that in. Now remember, the first thing that I usually like to do is figure out molar masses. And so I have one of our blue periodic tables here and a calculator, and I'm going to be looking at molar masses. So Fe, iron, it comes straight off the periodic table. It's going to be 55.8 grams per mole, rounded to 3 significant figures. Then we have oxygen gas. Individual oxygen has a mass of 16.0. O2 has molar mass of 32.0 grams per mole. Then we have Fe2O3, iron 3 oxide. A lot of you would use the table. I'm recommending that you stop using the table, and instead this is how I would do it. So I'm going to start with some parentheses, and this would go straight into my calculator. I wouldn't bother to write this down usually. Iron is 55.8 times 2 of them. 2 is the subscript. Close the parentheses. Plus oxygen is 16.0 times its subscript is 3, and this will give you the same molar mass as going a long way and using the table. So the molar mass of this one to 3 significant figures is 160 with a decimal point grams per mole. Here's the question: what mass of iron 3 oxide is produced from 65.2 grams of iron? As usual, we're going to start with what we know. This is in grams. It's a mass. In order to compare iron with iron 3 oxide, we have to use moles. So the first thing we have to do is divide by the molar mass of iron, 55.8 grams, and on top of that is 1 mole. Remember, it's 1 mole. The coefficient does not apply in the molar mass step. Now that we're in moles, we can use the mole ratio, and this is where the coefficients come into play. So moles of iron, 4. Moles of iron 3 oxide, 2. This is the only place where the coefficients appear in this whole calculation. So we have moles of this iron 3 oxide, but we want mass, which means we have to use the molar mass. Now that we're at this point, you can go ahead and put it in your calculator. Comes out to be 93.5 grams. Next question, what mass of iron 3 oxide? So we're talking about how much product in terms of grams is produced from, here's our reactant, 12.9 grams of oxygen gas. First thing, converted to moles. So we are dividing by the molar mass of oxygen, and that gives us moles of oxygen. Now we're ready for our mole ratio step, comparing moles of oxygen and moles of Fe2O3. Coefficient for oxygen is 3. Coefficient for the iron 3 oxide is 2. So this tells us the quantity of the iron 3 oxide, but we want mass. So we are going to multiply it by its molar mass, 160 grams. This comes out to be 43.0 grams. What mass of oxygen is required to rust a 45.2 gram sample of iron? So we have this iron, we want to make sure that it turns completely into products. So we have to have a certain amount of this other ingredient to make sure that happens. Same as always, start with the mass you're given, convert it to moles. Then my mole ratio step. Three moles of oxygen, 4 moles of iron. We are looking for what mass of oxygen, so we're going to convert it to grams of oxygen. And at this point, we're ready to go ahead and put it in the calculator. It is 19.4 grams of oxygen required to rust all of the iron in this sample. Here we have our double replacement reaction. It is lead-2 nitrate. Potassium iodide, and our products solid lead-2 iodide and aqueous potassium nitrate. Balanced. So as far as the molar masses go for this one, a little bit tight on space, so I'm going to erase a little bit. You can find somewhere to write. So when I'm doing one like lead-2 nitrate, I'm looking at my periodic table. I find lead, it's 207, and there's only one of them. And so it would look something like this for the lead, plus nitrogen is 14, and there are 2 of them. And then the oxygen, we can keep it fairly simple. So oxygen itself is 16, and there are 3 oxygens, times there are actually 2 of these sets. So it's 16 times 6, but I'm going to say 16 times 3 times 2. And this will give you your molar mass, which comes out to be 331 grams per mole. Potassium iodide is pretty straightforward. The only thing to keep in mind is to make sure that you are checking the formulas to make sure that they are correct. If your formula is wrong, your molar mass will be wrong. That means your number of moles will be wrong, and it snowballs really. Lead to iodide, 461 grams per mole, and potassium nitrate, 101 grams per mole. So at this point, we are set to go ahead and start writing these down. First question, what mass of lead 2 nitrate is required to produce 35.0 grams of lead 2 iodide? We've done most of the legwork already in terms of we have a balanced equation and we have all the molar masses. Now we just have to put the pieces together. So lead 2 iodide has a molar mass of 461 grams per 1 mole. Next up is our mole ratio step. We are comparing lead 2 iodide and lead 2 nitrate. And it is both of them have coefficients of 1. So we have moles of lead 2 nitrate. We are looking for mass in grams. And we already know the molar mass. It is 331 grams. Once you put it in the calculator, you'll find it comes out to 25.1 grams. And remember, it's important to label the substance because there are multiple substances in every equation, 4 in this one. And so we want to know which one we're talking about. So it's important to label it with chemical as well as units and your answer. What mass of potassium nitrate can be produced from 1.03 grams of lead 2 nitrate? First thing to do, convert it to moles. So we are dividing by the molar mass, 331 grams per mole of lead 2 nitrate. The next step is your mole ratio step. And we are looking for potassium nitrate. The coefficients for lead 2 nitrate is 1, for potassium nitrate is 2. That gives us moles of this product. We want grams. And its molar mass is 101 grams per mole. There again. And so we end up producing 0.629 grams of this aqueous potassium nitrate product. what mass of lead-2 nitrate is required to react completely with 30.0 grams of potassium iodide. We have two reactants here. We want to make sure that we allow this to react completely. We don't want to have leftovers of potassium iodide, and we don't want to have leftovers of the lead nitrate. So 30.0 grams of our potassium iodide. Remember, the first step is always to change it to moles. So we are dividing by the molar mass. 166 grams is 1 mole. Now that we're in moles, we're ready for the mole ratio. We are comparing potassium iodide and lead-2 nitrate. This is moles. So 2 moles of potassium iodide for every 1 mole of lead-2 nitrate. We have the right substance but the wrong units. We need to change moles of lead-2 nitrate to grams. So we are going to multiply it by its molar mass, 331 grams. We find that 29.9 grams of